Hello, welcome back. We're going to take a look at the explicit rule for geometric sequences. So remember, the purpose of an explicit rule over the recursive rule, the advantage is that it's more efficient. We don't have to have the previous term to know what the next term is going to be. So if we look at this, we have a sequence 1, 2, 4, 8, and 16. I can see that it's a multiplication sequence pattern. 1 times 2 times 2 times 2 times 2. So if I list all of the terms here, 1, 2, 4, 8, and 16, and then the number of times we multiply by 2. So if I look at this, I have times 2 0 times for the first one time to get 2, times 2 twice to get the 4 from the start, times 2 3 times from the start to get 8, times 2 4 times from the start to get 16. So notice that I've multiplied by 0 times 2, 1 time, 2 2 times, 2 3 times, and 2 4 times. So if we notice that if we look at the term number and compare it to the number of times we multiply by 2, the term number is 1, the number of times we multiply by 2 is 0. The term number is 2, the number of times we multiply by 2 is 1. 3, 2, 4, 3, 5, 4. If you notice, it's always 1 less. We are always multiplying the number of times by 2, 1 less than the term number. So if I want to find the 100th term, I need to multiply by 2 99 times. So for what do we notice about the number of times we multiply by 2? I notice that it's always 1 less than the term number. So let's take a look at our explicit formula for geometric sequences. And you might not have seen this before, so we'll break this down. So f of n, we have the nth term equals the first term times the common ratio n minus 1 times, and that's an exponent. So this n minus 1 up here, this is an exponent. So what that means is, for example, if I have 2 cubed, that's the number of times we multiply by 2. 2 times 2 times 2. 4 to the 5th. 4 times 4 times 4 times 4 times 4. That's called an exponent if it's up in the air. And so that's the number of times we multiply by r, which is the common ratio. So let's look at our first example. So we have a multiplication pattern, and you might have recognized this from before, but right away I see that the 1 is my first term. And then I also see that I'm multiplying by 6 every single time. So that means my r value is 6, my common ratio. So I know that I can write this as the nth term equals the first term times the common ratio raised to the n minus 1 power. So if I go ahead and write this, I have all the pieces and parts already. So I have f of n equals, my first term is 1, and I'm multiplying by 6 n minus 1 times. So if I want the 10th term, I will multiply by 6 9 times. If I want the 40th term, I'll multiply by 6 39 times. The purpose is we can plug whatever we want into n. So if we look at this pattern, I see that my very first term is 256. I also see that instead of multiplying, I'm definitely getting smaller, so I'm dividing by 4 or multiplying by 1/4. So my R value is 1/4. So I have our rule f of n equals the first term, 256, times the common ratio of 1/4 n minus 1 times. Looking at another example, I have the table and I see all my terms. The 27 is our first term. We didn't have to multiply by anything. We multiplied by 0 times. To get our next term, we multiplied by 1/3 one time. To get the third term, we multiplied by 1/3 2 times, and etc. Notice it's the same as dividing by 3, but we're multiplying by 1/3. And it's always the number of times is 1 less than the term number. So we know that any term we want, we can find that by taking that first term of 27 and multiplying it by 1/3 n minus 1 times. One less time than I want for the term value. Going down here, I have 6 is my first term. And to get my second term, I have to multiply by 10 one time. To get my third term, I have to multiply by 10 2 times from the beginning. To get my fourth term, I have to multiply by 10 by 3 times from the beginning. So my R value is 10. So for my explicit rule, I have f of n equals the first term times the common ratio of 10 n minus 1 times. Let's go ahead and find the first terms of the geometric sequence given this rule. So just by looking at this, I know that 3 is the first term. Notice the common ratio isn't in parentheses, but it very well could be. This 6 is our common ratio. So if I want to list the first 4 terms, I know that I'm going to start with 3, and I need to multiply by 6. 3 times 6 is 18, times 6 is 168, and times 6 is 648, and you can of course use a calculator. So to find the fifth term of this sequence, I have f of something equals 3 times 6 to the something minus 1. That n, I'm going to take 5 and plug it in. So essentially I have 3 times 6 4 times, because it's raised to the 4th power. I'm multiplying by 6 4 times. So this is equal, if you use your calculator, to 3,888. Notice how much quicker that was than using the recursive rule. I could, of course, multiply the 648 by 6 as well, but this sometimes is faster. So for the 9th term of the sequence, I have f of something equals 3 times 6 to the something minus 1. How many times am I going to multiply by 6 from the start? Well, 9 minus 1 is 8, so it's 8 times. So I have 3 times 6 to the 8th power, which is a large number, 5,038,848. Here's another one for you to try, and I hope that you guys have a wonderful day.